Okay, so this is atomic interactions lab. Okay, we'll see what happens to the atoms when they come close to each other, and actually, most importantly, we'll try to understand why the atoms combine to make molecules. Okay, um, so here you can select two different atoms. Here we have selected, right now we have neon as the two atoms. Okay, there are two neon atoms right here, and you can select it to argon or oxygen, or you can mix and match basically, so you can change different atoms. Okay, and what happens is that this is the energy diagram basically. As you go on the y-axis, you have potential energy, and on the x-axis you have the distance between the atoms. Okay, so the first atom, so this atom is right here at the bottom. Okay, and when you bring the atom close to, so this is the distance between the two atoms, and when you bring this atom close, what happens to the potential energy of the atoms? Okay, that's what it shows. Alright, so the first we'll do with oxygen. Okay, two atoms of oxygen will separate. This atom is pinned, it's fixed, you can fix it. You can fix the other atom, doesn't matter. Yeah, so you can select which atom you want to fix. In this case, oxygen is the fixed atom, the other oxygen is movable, you can move. And so let's start at this point. You can see that the distance between the two atoms is huge, correct? There is absolutely no interaction between these two atoms. There is no attractive force, there is no repulsive force between these two atoms. Yeah, there is absolutely no interaction between these two atoms, correct? At this distance. Yeah, okay, now what we'll do is we'll select from here, show forces, we'll select component forces. Okay, there are two types of forces: the attractive forces that we talked about in the class, and there are also repulsive forces. Okay, now the attractive forces are, what are the two attractive forces in an atom, in between when the two atoms comes together? What are the two attractive forces? Do you guys remember? The two attractive forces are nucleus electron attraction of one atom, and similarly nucleus attraction electrons of the other atom, correct? Yes, no guys? I can see what you're typing. Alright. What are the repulsive forces? There should be a repulsive force, the electron repulsive force, and there is also nucleus repulsive force, correct? These two forces are going to repulse each other because electrons are negatively charged, and electrons on this atom also negatively charged, and negative charge of these two atoms will repel each other. Similarly, nucleuses are also positively charged, and they are going to repel each other. Yeah, alright, so let's start. At this point the potential energy, let's say, is 0 for um, all practical purposes. Yeah, and now as you start to bring the atom close to the other atom, see what happens at particular distance. Yeah, you'll see that, so at this particular, sorry, so at this particular distance, so you need to pause the animation, otherwise it just goes automatically. Yeah, so you need to pause the animation. So at this particular distance, you see that little yellow arrow is coming up. Do you guys see that? Okay, and the yellow arrow is basically the attractive force, van der Waals attractive force, correct, between the atoms. So you can see the nucleus of this atom is attracted towards the electron of this atom, nucleus of this atom is attracted towards the electrons of this atom. And remember that nucleus is really small as compared to the atom, so most of this space is empty. Yeah, so all this space right here is empty, most of the atom is actually empty. Yeah, and as that attractive force starts to come into play, you can see that the potential energy of the system decreases. Yeah, it has start to decrease as you bring the atoms even more close to each other. You can see that the attractive force increase and the potential energy decrease even more faster. At particular distance, at this particular distance, you will see that the pink arrow has started to come into play. Do you see that? There is a pink arrow here, and there is also a pink arrow here, which is kind of hard to see because it is hidden behind this yellow arrow. Yes. Yes, guys. Okay, so now that pink arrow is basically the repulsive force. Yeah, so the attractive force has increased, at the same time the repulsive force has started to come into play. It's very little as compared to attractive force, and as a result the atom will move even more closer to each other, and as they move you can see that the repulsive force has increased significantly. Yeah, at this point the attractive force is still larger than the repulsive force. As a result of that, the atom will keep on moving closer to each other. Is that clear? Yeah, and see what happens to the potential energy. It has decreased significantly from the value 0. Yeah, it is decreased significantly. Now you bring the atom closer and you can see that now the attractive force, now the repulsive force is increasing much faster than the repulsive what I'm saying, the repulsive force is increasing much faster than the attractive force, and at particular point they are going to be equal. Do you see that at this point? I mean, now this arrows are beyond the screen so you can't really see, but at this point trust me that both the arrows are of equal size. That means the repulsive force and the attractive force are same at this point. Now this is the point where you have the lowest potential energy, correct? Okay, the potential energy of the system is the lowest at this particular point. Now if we start to bring these atoms even closer, see what happens. We bring the atoms even more closer. Now the attractive force is not increasing, in fact the repulsive force is becoming increasing much faster. You can see that the energy increases even by slight change actually. So from here to here it decreases much faster, and then it increases, starts to increase much faster. So this is the bond length of the atom. If you take here and see that the nucleus, the distance between this nucleus and this nucleus, this is the bond length of the atom, or the center of the atom. Is that clear? If you bring the atoms any closer, the repulsive force increase much faster, because there are the nucleus repulsions and the electron repulsions becomes a major factor after this point. As a result of that, the potential energy increases. So molecules can't be any closer. Yeah, okay, now you can see that the drop in the energy is much significant in this case. Yeah, but it's not always the case. This is an oxygen molecule, and we know that oxygen is a is a stable molecule. The bond between two oxygen atoms are much stronger bonds, correct? The bond length in fact is a very short bond length, right? Between the two atoms is a short length. Now if you let the go, you know, you can see this animation. Basically you let go this thing, not here. So you'll see that it goes. Now that's the bond length. It basically vibrates. I don't know if you guys can see it, but do you guys see it? That's kind of the molecule is vibrating. Yeah. So what is happening here? As the repulsive force starts to increase, the molecule will move back, the bond length will increase, and at that point again the potential energy start to increase, right? And at that time the attractive force will increase and bring the molecule together. Once the molecule comes together again, you know, the potential energy start to increase, and so that's what happening. The molecules are constantly vibrating. Yeah, the bond length is not a fixed bond length, it's an average bond length. Okay, so the average distance between these two atoms is the bond length. Yeah, it's not a fixed bond length. And that is the case in any molecule basically. Yeah, so shorter the bond length, stronger the bond; longer the bond length, weaker the bond. That's kind of like a general expression here. Is that clear? Okay, all right, so let's change the atom now to, let's say, neon. Now here you can see that the drop in potential energy is not as much. You can you know, do the same experiment. You can bring the molecules together, and when they start to come closer, obviously you can see now here. Let me turn on the component forces. Attractive and repulsive, same. Yellow arrow is a attractive force, and pink arrow is a repulsive force. Okay, so as they starts to come closer to each other, the attractive force, now you can see that the little yellow arrow has started to show, correct? And as they come closer to each other, you can see now that the pink arrow has also started to come. Yeah, and at this particular distance you can see that has reached its bond length, has reached the lowest potential value. The forces have balanced each other. The attractive and repulsive forces are balanced, and this is the bond length. Yeah, if you bring the atom any closer to each other, you can see that the repulsive forces starts to increase much faster than the attractive force, and as a result the potential energy increases. Yeah, now when that starts to happen, obviously the molecules, the atoms will start to move away from each other, and at this particular point again they will have the equal amount of attractive and repulsive force. Okay, and since they are moving, it will move. Now the attractive and repulsive forces start to decrease. Now you can see at this particular point the attractive force is larger than the repulsive force, and so they will move closer to each other. Okay, so they again same phenomena will start to vibrate at the particular point. You can see it's actually, so it will basically start to vibrate at this particular point, and that's your bond length. Is this clear? Okay, and what would be the significance of the potential energy drop in this case? Now the potential energy drop is not as much as in the previous case. As a result, you can also see that the overlap of the atoms, yeah, is not as much. The orbital overlap is very little as compared to oxygen. Yeah, and that therefore you can say the potential energy drop is also less. If the overlap would be more, then the potential energy would drop more. Okay, or vice versa, you can say since the drop in the potential energy is less, the orbital overlap is also less. Okay, it's a small overlap, and as a result, what do you think about the bond strength? Is it going to be a strong bond or a weak bond than oxygen? guys? Is it going to be a stronger bond or a weaker bond than oxygen? Rashi, that is correct. Devangi, more is not the correct term. Stronger would be the correct term. Yeah. So that's correct. So stronger bond, yeah, because the overlap in this case. Now this is, I'm sorry, what I'm saying. This is going to be a weaker bond, yeah, than oxygen. Yeah, I was not paying attention. I'm sorry. All right. So is this a stronger bond? No, this is a weaker bond than oxygen. Yeah, because the overlap is very little as compared to the oxygen overlap. Correct? And this is in fact the case. The neon is actually a gas molecule. Yeah, it's an individual atom, and this is actually at lower temperature, so that forms a molecule. But neon is a gas. Yeah, same thing is argon is a gas. It's an individual atom. They don't form molecules. Yeah, because the overlap is a weak overlap, and as a result, the bond itself is a very weak bond. Okay, very weak bond actually. Yeah, same thing with argon. You can say they have slightly larger energy drop, and as a result, they have slightly larger bond length. Yeah, so that's right here, you can see that. Okay, slightly larger than neon, and because the nucleus is larger, the charges are more with argon. Yeah, argon is right below neon in periodic table, and as a result, argon is a larger molecule, and because it's a larger molecule, there is a slightly more overlap, but it's not as much. So you can compare oxygen. In oxygen, there is a huge drop in the potential energy, but in argon and neon, it's not. So this is the driving force for. So argon and neon does not form molecules. Correct? They are gases. They are atomic gases at room temperature. Okay? They do not form molecules because the gain by forming the molecule is a very small gain. The potential energy gain, when the potential energy drops, that's the profit for atoms. That's the profit for the molecules, correct, to combine. And this profit is actually a very less profit, and as a result, they don't form molecules at room temperature. They are atomic gases at room temperature. Whereas for oxygen, you can see the drop in potential energy is much larger, and therefore oxygen cannot exist as atomic as atom under any circumstance. Yeah, when you have two oxygens in the vicinity of each other, they will combine and form a molecule, oxygen molecule. Yeah, is that clear? Okay, so what are the conclusions of this experiment? What can we say? We can say that if the overlap is large, then the bond strength is also large. Correct? If the overlap is weak, then the bond strength is also weak, or the bond is also weak. Yes? Okay, if the bond is strong, then you can say that the drop in potential energy is also large for a strong bond. If the bond is weak, then the drop in the potential energy is going to be small. Yes? And if the drop in the potential energy is small, then the atoms may not combine to form molecules. If the drop in potential energy is significant, then the atoms may combine to form a molecule. Okay, Also you can say you can so here you saw the forces, right? At this time, at this point, you saw the forces are much larger, both attractive as well as repulsive forces, correct? They are both the forces are quite large at this point. Yeah, the forces, you can see the magnitude of the force is so large that the forces are going out of the screen in case of oxygen. But if you go to argon, or you can see that that is not the case. Yeah, the forces are right within the screen. Same thing with the neon, the forces are right within the screen. Okay, so what can we say about this? We can say that the magnitude of the forces is also related to the strength of the bond. Okay, strong bonds will have strong forces, weak bond will have weak forces, both attractive as well as repulsive forces, correct? Okay, so that's one lab. So let me close that and get another lab. This is called as um, Rutherford's scattering experiment. Okay, and so we talked about Rutherford's model in the class. Do you guys remember that? Rutherford's scattering experiment. So this is the animation for that. Now here we have both the models, Rutherford's atom and also plum pudding model. So we're going to do both today. Okay, and this is a typical atom. Okay, this is actually the part of the atom, just the focus on the nucleus. You can see that on the periphery there is an electron that is going around. You can see that. So that's, you can see that one electron, this is the first orbital, and the one electron that is revolving around. Obviously, you know, this is a large atom, so it will have more orbitals, more electrons, and this is quite a big atom, correct? So now, I mean, you don't see the other orbitals, but you can imagine this is the first orbital, so the second and third and the fourth and fifth orbitals are going to be much farther away from this one. Okay, just to give you a perspective that this is a nucleus, and far away distance from the nucleus there is this first orbital in which you can see the electron revolving. All right, and now this is our instrument. This is where you have the gold foil. Okay, this is the gold atom. You can see that from the atomic properties. You can actually change it to different atom, but since Rutherford used gold foil, we are also using the gold foil. Okay, now this is the number of protons in gold, these are the number of neutrons in gold. Okay, these are the legends for the electron, proton, neutron and alpha particles. Okay, and we're going to use the energy of the alpha particles as max. Alpha particles are right here, you have generated in here alpha particle. Okay, and as soon as you turn on the gun, you press the button here, the alpha particles will shoot and it will go through the slit into the gold foil, and you know, it will scatter, and you'll see the little dots on the screen, correct? That's Rutherford's experiment. Now what we'll see is what happens to the alpha particles when they come close to the nucleus. Okay, that's what we're gonna see. Is the setup clear? Any doubt here? Okay, so we're gonna turn on the show traces. Okay, so click tick this box called show traces. It's very important, so it will show you the traces of the alpha particle. Rashi, you have doubt. Harshad, you have doubt. Okay, what is it? Do you want me to repeat the setup? No doubt. Okay, Devyangi, you also have no doubt. Okay, okay, I'm sorry, misread that. I thought I asked you, did you understood? Anyway, not important. All right, so let's start our experiment. We you know make sure that the energy of the alpha particle is max. We have clicked our show traces. This is for gold atom, yeah, the number of protons and neutrons. And let's start. You can see the alpha particles are coming in, and you can see what happens to the alpha particles as they come close to the nucleus. They deviate, correct? This is actual Rutherford's experiment. Okay, so let me pause it for a second. So let's just, isn't that cool? Yeah. So alpha particles, we know, are made up of 2 protons and 2 neutrons. They do not have any electrons, correct? They are positively charged species. Nucleus is also positively charged species, correct? We know that it's made up of protons and neutrons, and in this case we have 79 protons and 118 protons. So there are quite a few number of protons in the nucleus. Yeah, 79 protons or 79 positive charges stacked up in this little space. Okay, and so as a result, when these positive charges come close to this nucleus, okay, they are going to get repelled. Yeah, so you can see that if the particle is far, then it's good, it gets repelled a little, but if it's coming like a head on, you can see that it gets repelled almost by 90 degrees and even more. Some of these particles, like, so this particle is going to get repelled even more. So let's start our animation and see. So you can see that this particle actually came right here, correct? So this particle is gonna come, so this particle is gonna face a large number of positive charge. So that should come right back. Okay, so let's start our animation. You see that comes right back. Okay, only the particles that are at the periphery of the box, they go straight. So you can see that these particles, they are the ones, they are going kind of straight or straightish, you know. The farther particles will probably go straighter, I guess. Is this clear? Yeah. So this is how Rutherford came to the conclusion that that the positive charge or the protons are actually stacked up in a little place in the nucleus. It is not spread up over the entire atom. The that was proposed in the Plum pudding model, correct? So what would happen if you had a Plum pudding model? What would happen? I'll show it to you in just a little bit. Okay, so let's go and we'll come back to, I think, Rutherford atom a little bit later. Okay, so let's go and look at Plum pudding model. Okay, so we'll have max energy here. We'll click on the show traces. This is the Plum pudding model. This red area, okay, is the entire atom, you can think. Yeah, and this is the positive area where the positive charge is dispersed, and this little dots on it, these are the electrons. Okay, and that was the Plum pudding model, that, you know, nucleus is there, sorry, not the nucleus, the positive charge is spread up over the atom and the electrons are embedded in that plum. Okay, so let's say you have this model, and let's start our Rutherford experiment here, and let's see what happens. You can see that there is absolutely no deflection. The alpha particles are going straight through. Do you guys see that? Yeah, and the reason is again because you see here the positive charge which was saturated at a very small position in Rutherford's atom is actually now spread up over a very large area in this model. Correct? It's a large area over which the positive charge is spread. Now, and combine that with this little electrons which are spread all over the place. Yeah. Now this, what this tells you, that the whole atom is actually neutral. That's correct. That would be a correct prediction, and that's why this model was actually proposed. But because the electrons are spread up all over the atom, yeah, this would actually decrease, or this will make the whole thing as neutral. Correct? The whole thing, the whole atom is going to be neutral. In effect, the positive charge is going to be negated by these presence of electrons all over the place. As a result of that, these alpha particles are going to go straight through. They are not going to interact. They are not going to experience any positive repulsion from this area. Okay? Is that clear? Harshad? Okay, alright. So that's plum pudding model, yeah, and that explains to you what is going on, correct? Let's go to Rutherford's atom again, and you can see that the atoms, you know, this positive charge is saturated in the center, and so it's a very small area over which this large number of protons are saturated, and as a result of that, these alpha particles are going to get repelled by this large positive center. Okay, now let's change the atom. Let's reduce the number of protons in here. Okay, so we'll just make it like least number of protons, 20 protons, and let's say 20 neutrons for all practical purpose. Okay, and we'll start. Everything else is same. The only thing we have done is we have selected a smaller atom, and now let's start the Rutherford experiment. What do you say about the deflection in this case? Do you think the gold atom, what do you think? What do you compare the deflections? How would you compare the deflections between the gold atom and this particular atom? Is it more, less, different? How would you categorize? Would you say that most of the, it's very small in this atom? That is correct, Harshad. Yeah, the deflection is very small in this atom. You see that most of the atoms, most of the alpha particles, they are going straight through. Yes, only some that are, even the ones that actually come close to this atom, they actually don't. So you can see right here. Yeah, so these, even the ones that are close, that comes close to this nucleus, they don't deflect as much as was the previous case. And even the far ones were getting more deflected, right? In this case, they don't get deflected as much, and that's because the positive center is not saturated here. Yeah, the positive charge is not as concentrated, and therefore the reflection is not as much. Okay, so it totally depends upon the atom and its size and how much positive charge is in the nucleus. Is this clear? Is Rutherford's model plum pudding model, both of them clear. Okay, all right, so last experiment we're gonna do is build an atom. Yeah, it's a very simple experiment, really. um, we have done this before, correct? You guys have built the atoms before, Divyangi? Okay, all right, so we'll do it slightly differently this time. Let's click on symbol, mass number, and the net charge. Okay, and let's put proton in the nucleus. Immediately you see that this is a hydrogen atom. It's actually a hydrogen ion, correct? There is one proton and you get one electron and you get hydrogen. Okay, you see that hydrogen has one proton, its mass number is 1, atomic number is 1, and symbol is 0. The charge is 0 on this one. If you remove the electron, obviously you get one charge. Is that okay? Understood? Hydrogen atom. Now, what is this orbit? What do we call this orbit? This is K orbit, correct? First orbit is also called as K orbit. How many electrons it can occupy? Can occupy 2 electrons, correct? Very good. Okay, and it only has 1 electron in it. Is it going to be a stable atom? No, right? It is not going to be a stable atom, and therefore hydrogen atom does not exist. Yeah, it never exists. It basically exists in theory, but that's the reason why you have H2 molecule, hydrogen gas. It exists as a hydrogen gas, but hydrogen atom actually does not exist. Okay, now let's add one more. Hold on a second. Yeah, so let's add one more electron. Now you got 2 electrons in the atom. Do you think this will exist? Hydride ion. This is actually called hydride ion. There is a negative charge on this hydrogen. Do you think that this can exist? Yes, no? Yes, that is correct. It actually does exist. Okay, it's not a very stable molecule, but the idea that it exists in solutions, you can actually do reactions with it. Yeah, and it does exist as a strong base. Okay, now let's take out 2 electrons, both the electrons from here. Okay, now this is a hydronium ion, correct? It's H plus ion. What about this? Do you think this will exist? This has, again, you can see the charge on this one. It has a mass number of 1, charge plus 1. Okay, do you think this exists? Divyangi? No, it does not. Yeah, it does not exist. This is called as proton. Protons do not exist. We saw that in chemistry, that when you write protons, you actually have to write it with water molecule as hydronium ion. Okay, so proton exist as hydronium ion, but they don't exist as by themselves. Okay, so when you add, let's say, HCl in water, um, the proton from the HCl does not exist as it is. It exists as hydronium ion, combines with water, and exists like that. Okay, is that clear? Okay, now add one more proton to it and set two neutrons. So this is helium atom, correct? You add two electrons to it, two protons to it. So this is a neutral helium atom. There is no charge. All the charges are balanced here, correct? So this is a helium atom. See that the number of protons and number of electrons needs to be balanced for an atom to be considered a neutral. If you remove, let's say, one electron, so if you want to see the alpha particle, yeah, this is alpha particle, basically that's what it is. This is an alpha particle, and a helium ion, 2+ ion. Yeah, so, and this is a neutral helium ion, neutral helium atom. Okay, now you see that the k orbital here has two electrons in it, so that means that this is a completely filled k orbital. L orbital is completely empty, therefore this is a stable molecule. Yes, helium is in fact a noble gas, which is on the far right side of the periodic table. It is completely unreactive, and does not react with anything pretty much. And that's because it has this two completely filled orbital, and two electrons in the k orbital. It is completely filled. It's stable. Is that clear? Okay, if you remove one electron, obviously you get an unstable species, which is helium ion. Yeah, you remove another electron, you get alpha particle. Okay, let's build lithium. Okay, you add that, and so you add two electrons. Now you added two electrons, it is still an ion. Okay, so if you add the third electron, where it's gonna go? It should go to the next orbit, correct? L orbit. Yes, that is correct, Harshad Divyangi, and that's what happens. It's a neutral atom. Is it a stable molecule? Is it a stable atom? Well, it is stable, but it's not very stable, because the L orbital occupies 8 electrons. It has only 1 electron in it, and as a result it cannot exist as lithium atom. Okay, it exists as metal, where the electrons are shared, but it does not exist as lithium atom itself. So we can have, like the way helium atom exists, lithium cannot exist as atom. Is this clear? Okay, if you remove this electron, now actually you have lithium ion. Do you think this is stable? It should be stable, correct? It has the inner orbital, the k orbital is completely filled, the l orbital is empty. Doesn't matter if it has a charge or not, it's really the charges are only for neutrality. Okay, the stability comes stability of the atoms actually comes from the fulfilled orbitals. Okay, if the orbitals are filled, fully filled, then the atom is going to be stable, otherwise it's not going to be stable. That's pretty much, that's the bottom line of this experiment. Yeah, the ions are basically, if the charges are imbalanced, then you will have ions, and so it has nothing to do with an atom being stable or not. Lithium ion is in fact stable and exists in solutions, and we do reactions and stuff. So the tendency of the lithium, neutral lithium atom, is to lose this extra electron as soon as possible so that it can gain the stability. Okay, clear? Okay, let's add back that electron, and now we add one more neutron. Okay, we added neutron. You can see the mass number has increased to 7. Okay, so this is still a lithium atom. What is the difference? The difference is of one neutron. Nothing else has changed. The charge has not changed. Yeah, the charges are not changing. Number of electrons are not changed. The properties of the atom has not changed, correct, because the number of electrons are still same. Nothing has changed. The only thing you have done is added one proton to it. What do you call it? What is the relationship between the lithium 6? So this is lithium 6, okay, and this is lithium 7. What is the relationship between lithium 6 and lithium 7? What are they called? Isotopes. Do you guys remember that? Okay, so they are called isotopes of each other. Okay, this is the similar as, you know, even hydrogens have 3 isotopes, so we can quickly construct that. Yeah, okay, so this is your normal hydrogen. You add, so this is actually called a deuterium. This is a hydrogen isotope, and this is tritium. This is a unstable hydrogen isotope. Yeah, these are, all of them exist actually. Yeah, and these are called isotopes. Deuterium is actually naturally abundant, so in all hydrogens, and even in the water molecule you drink, there are some deuteriums. Some of the hydrogens are actually deuterium in there. Okay, you can actually buy a vial of this water. This is called as heavy water because it has mass that is twice the mass of normal hydrogen, correct? Its mass is doubled. The charge and all the other things are same. The reactivity, the properties are same. Only thing is the mass has doubled. Okay, so this is why if you make a, instead of using normal hydrogen, instead of using this hydrogen to make water, if you use this hydrogen to make water, the water itself is called as heavy water. It is actually you can actually buy a vial of 99.99% pure deuterated water. Okay, there's also tritium water. You can buy this tritium water. Oh, no, not that. Okay, you can buy this tritium. It's very expensive. Deuterium itself is very expensive. Tritium is like super expensive. But they used to do this various different reactions. Use deuterated water. You can deuterate pretty much anything using, if you have the water, you can do reaction and convert any normal hydrogen compound into deuterated compound, yeah, for research purposes. But it's not harmful. It doesn't do anything to you if you drink deuterated water. It's just like normal water. Yeah, it's pretty much the same thing, but it doesn't kill you. Okay, so let's now talk about, so we'll look one more molecule, 5 or maybe 10 more minutes. So add like 4, 5, 6, 7, 8. 1, 2, this is 4, 5, 6, 7, 8. Yeah, and so we add electrons to it. So you can see that any electron we add after 2 actually goes into the second orbital. Okay, alright, so how many electrons oxygen have in its outermost orbit? This is a neutral oxygen atom, correct? It has 8 protons, 8 neutrons, mass number is 16, atomic number is 8. The net charges, you can see the protons and neutrons are balanced, so the net charge is 0. How many electrons there are in the outermost orbit? Six electrons. Okay, how many electrons it would require to gain the stability? Two electrons. How many electrons it would require to lose to gain the stability? That is correct, 6 electrons. Now what is easier, to gain 2 electrons or to lose 6 electrons? That is correct, to gain 2 electrons, and that's exactly what happens. Okay, now oxygen with 6 electrons in the outermost orbit is unstable. Oxygen does not exist as atomic oxygen, correct? It exists as molecular oxygen, O2 molecule. It exists as ozone, O3 molecules, but it does not exist as oxygen atom. Okay, that's because it has an incomplete second shell. Okay, it requires 2 electrons, and it can easily gain 2 electrons to complete the octet, because that's the easiest job to do. So this is an oxide ion. You can see that the total charge on the oxygen is 2. These are the excess of the electrons. Total charge is -2. Mass has increased, mass has been same. Yeah, it's 16. We didn't do anything to the center. Okay, so this is oxide ion. Okay, this is how atoms and ions are actually formed. Let's look at one more really quick thing. How is O3 stable? Well, in O3 all the 3 atoms actually have an octet. they combine in such a way that they form an octet. There is a lot more to it. I really don't want to go in more detail because I'm gonna have to use whiteboard and stuff right now, yeah, which I can't do. Okay, it's a charged molecule though. It's not a neutral molecule, it's a charged molecule. Okay, but O3 is stable. Okay, Arshad. Okay, maybe I'll explain to you some other time. Yeah. All right. So this is carbon. It has 6 protons, 6 neutrons. You can see the first orbit has 2 electrons, and the second orbit has 4 electrons. Okay. So what is easier for oxygen, to gain 4 electrons or to lose 4 electrons? Divyangi? The correct answer is neither. Okay, it's not easy for oxygen to either gain 4 electrons or lose 4 electrons. Okay, it actually shares 4 electrons with other atom. For example, CH4, it's gonna share 4 electrons with hydrogen atom. Okay, so the 4 hydrogen atoms brings 4 electron. It already have 4 electrons, and that's the way it would complete its octet. This is called as covalent bonding. We're gonna see that next year about covalent bonding. Yeah, so it actually gains 4 electron by sharing its 4 electrons with other atoms. Okay, is that clear? Neutrons, they are for stability. So I mean, I don't know, let's look at what is the question. How is lithium stable with 4? Okay, so this is lithium, normal lithium, you can say. This is isotopic lithium. This is actually more stable than lithium, lithium 6. Okay, lithium 7 is actually more abundant than lithium 6. Neutrons, actually the more protons you have, the more neutrons you need for stability. The whole job of the neutrons is to stabilize the atom, stabilize the nucleus. So if you look back in the gold atom, gold had 79 protons, and I think it had, I forgot how many neutrons it had. Do you guys remember? Do you guys remember how many neutrons gold had? 118 neutrons. Okay, so that how many neutrons it would require for stability. Okay, so neutrons are there for stability. That's pretty much it. That's their whole role in an atom. Protons are for charges, and electrons for neutrality, chemical properties. Is that clear? Okay, the more protons you have, the more neutrons you would need for stability. That is kind of like the general rule. As you go from atom to larger atoms, you would require actually more neutrons. Okay, so I think in terms of odd number of electrons, I think lithium is the first element where you have more number of neutrons than protons. Okay, before lithium, all the other elements have equal number of protons and neutrons except hydrogen. Hydrogen does not have or you know, hydrogen does not have a neutron. But other than that, all the other 5 elements actually have so lithium, so 4 3 4, yeah, so all the other elements actually have. So from lithium, I don't know what is the next element. It doesn't come. I'll have to look at the periodic table, but I think potassium or calcium after lithium has more number of neutrons. And so as you go down the periodic table on this side, the difference in the number of protons and neutrons increases. Yeah, I don't know. Sodium, I think sodium has 23, right? Sodium is 23. Yeah, so it does have after lithium, it does have sodium would be the next element to have more neutron for stability. Okay.